Good morning, Astronomy 1020. Welcome to your 13th lecture series where we're going to be discussing the end state of stars. We got a little bit of nuclear fusion to clean up as well. And today we'll be doing a lab called the Period-Luminosity Relationship. It involves plotting some points. So get your best plotting brain in order here. In our last lecture, we learned about general relativity, about how mass bends and warps space-time, and then other masses move along a curved four-dimensional space-time to fulfill their gravitational orbits. It's kind of a geometric view of gravity, pretty weird stuff. That's going to come in handy today because it turns out that when the highest mass stars run out of nuclear fuel, they've got so much mass that they can't stop a never-ending gravitational collapse that, in theory, will smush all of the matter of the star into a singular point particle, a singularity, which is what we call a black hole. And that's stuff that's, you know, we take an astronomy class so we can talk about fun stuff like that. Yeah. In fact, it's probably extremely hot if you're just talking about temperature. You know that as you confine a gas to a small region of space, its temperature tends to go up. Now, I believe that y'all made a little chart for me in a week ago, well, let's see, 2 weeks ago on Thursday. You guys made a chart showing the evolution of high mass stars versus low mass stars. Yeah, Austin, there is a way to put you on the TV. You just, you have to connect your, yeah, an HDMI cord, man. Just plug an HDMI into your computer. If you have a phone, you need a little widget or dongle. So I don't know if you've got that dongle, but.
I'm glad you know the name of that, Professor.
The name of what?
Dongle.
Because I'm an AV nerd and I grew up playing with VCRs and TVs and projectors. And I know the name of every stupid cable and the name of any little dingly wingly widget like this thing that holds my USB cables is called a dongle. So I don't know. It's because I'm 42 and I'm, you know, I've just been around the block. Okay. So anyways, I know, don't remind me. Okay. Anyways, let's get to this here. Let's talk about the end state of stars. You guys will remember that there's kind of three classes of star. There are low mass stars, intermediate mass stars, and high mass stars. I always like to start my day with a question just to see if you guys remember any of the things that I say to you. So why don't you guys tell me about the mass ranges of low, intermediate, and high mass stars? And you got to be careful here because a one solar mass star is not an intermediate mass star. Do you guys remember? In fact, let's start today with notes. We're going to do, today's lecture is on a little more fusion in stars and then a lot about the end state of stars. So there are three sort of mass ranges for a star. And the reason why we have to classify stars into one of three ranges. Oh my gosh. I know. I'm becoming an older man. Anyways, well, it hasn't been from treating the temple right. I'm going to tell you that. Okay. The reason why we need three different mass ranges for a star is that it turns out stars undergo different types of fusion depending on which class they're in, and then they die in different ways. Actually, intermediate is the stupidest mass class because it's kind of a hybrid of the other two. I'm mostly going to be focusing on high mass versus low mass, but we're going to do it right for starters here. There's high mass stars. There's intermediate mass stars, and there are low mass stars. And I want you guys to tell me what the ranges are from your notes. Can you do that while I sip coffee? These questions are an elaborate ruse for me to caffeinate up while we're having class here. You'll have to go before your relativity lecture to find it. No one? What's the lowest mass a star can have? What's the highest mass a star can have? Arunsak.
I got the notes. Low mass is 2 solar masses to 0.1 solar mass.
I'm going to start on the small.
And intermediate goes from 2 to 8 solar masses.
Yep.
And then high mass goes from 8 to 100 solar masses.
Right. You'll remember that stars can't really get too much more massive than 100 solar masses, or they will blow themselves apart due to radiation pressure. So that's getting close to the so-called Eddington limit for stars. The Eddington limit is the highest mass a star can have before it shines itself apart. And down here, this is the limit needed for nuclear fusion. This is the lowest mass needed for any type of fusion. Why don't you guys jot those down again in your notes? I don't think you can write this enough. All right, we covered the low mass star a little better than the high mass star, but that being said, why don't we review the low mass star quickly, then the high mass star, and then we'll start focusing on their death states, so to speak. Clearly, our sun, if you think about it, students, is a low mass star. Are there more low mass stars in the universe? Well, let's forget about the universe. Let's talk about our own Milky Way galaxy. Are there more low mass stars or high mass stars in the Milky Way galaxy? What do you think?
Low mass.
Very good, Kaitlyn. And that's, I was seeing if you guys remembered that we had learned about the initial mass function. Astronomers asked themselves this question, so they went out surveying and counting the numbers of stars, and they discovered many more low mass stars than high mass stars. Nature is weighted towards these fuel efficient stars rather than these big gas guzzlers, okay? And there is an analogy with cars, right? Low mass stars live for a very long time, so they're kind of like the, you know, the, I don't know what you want to, actually, I'm not really much of a car person, so I'm going to flounder here, but some kind of a Hyundai or a little fuel efficient, you know, Japanese style car. They might, these low mass stars, they burn their fuel very slowly because of their lower gravity, and they can live for 10 to the power of 11 years. Someone translate that into normal English for me. What does 10 to the power of 11 mean? Test your scientific.
Trillion.
False. Trillion is 10 to the 12.
Really?
100 billion.
100 billion. I would look at 10 to the 11 and I would say, if you have one, let me just show the whole class how we did that. 1 times 10 to the 11 is the same as 10 times 10 to the 10. I'm not good at handwriting on this thing, which is the same as 100 times 10 to the 9, right? So it's 100 billion, okay? Do you see how my logic there? Probably not. Okay, anyways. A O or a B type star is kind of like a gas guzzling Humvee or something. This type of car, this type of star rather, lives for 10 to the power of 7 years, which is how long? In English?
10 million.
10 million years, right? That's a crazy difference in lifespan. These things burn out so fast. Galaxies, there are different time scales in nature. Um, the time scale of a human life is close to 100 years, right? The time scale over which the Roman Empire might last could be 500 years. The time scale over which a geological event might take place, like shifting plate tectonics, could be 100 million years. The time span over which you get bored could be about 3 or 4 minutes at best, right? Now, the time span over which galaxies evolve are in the giga years. They're in the billions of years. So galaxies don't change very much over the course of 100 years or even 1,000 years. You have to think sort of a little bit more cosmically in terms of time flow. For an astronomer, 10 million years is considered a short period of time if you study stars. This is a short lifespan. 100 billion years is considered a long lifespan. How many of you know how old the universe is? How long is the universe itself? Okay, fine, Christopher. You know what? I said 500 years. I'm off by a factor of 3. Astronomers consider any guess that's within a factor of 2 or 3 to be accurate. Low precision science. Okay, so anyway, but thank you, Christopher, for that correction. He's reminding, by the way, for the nighttime students, he's reminding me the Roman Empire lasted 1,500 years. I was kind of winging it there. So listen, right, Arunsak knows that it's the life of the universe is about 14.6. Actually, I think it's been downgraded to 13 billion years after the. You guys might remember I told you about that parallax satellite called Gaia. So Gaia has helped to change that. Age of the universe, 13.77. So your number of 14 was actually better than mine. 13.77 billion years. It's amazing that we know it to the 4th decimal place, if you think about it. Astronomy used to be a low precision science, or cosmology used to be a low precision science, but it's improving. Does it seem weird to you guys that a low mass star could live for longer than the age of the universe? Does that trouble you in any way? Is that okay? No, it's not okay, says Runsack. It means there should be some stars that haven't died out yet. Anyways. All right. Let's talk about the lifespan of a low mass star. A quick recap of the light. No, the look back time is another thing you shouldn't be confused about. I'm just trying to say that the universe can be 14 billion years old, and there can be stars that have a lifespan of close to 100 billion years. It just means that those stars have not died yet. Some astronomers believe that there should be stars left over from the very beginning of the universe, from the first wave of star formation. And those are referred to as population 3 stars. We have never detected such a star. And I'll say more about that at a better time. Okay, let's talk about the lifespan of a low mass star, a 1 solar mass star. The life. See, we want to talk about the death of stars, but you kind of have to remember everything that led up to it. And I think between your turkey tryptophan and our relativity discussions, you might have forgotten some things and need a jog, okay? The life cycle of a 1 solar mass star, and this would be considered a low mass star. And you can use that little cheat sheet table that I developed with you guys if you want. So remember that I'll get you started. They begin their lives as a protostar. And in the protostar stage, there's no fusion at work. Eventually, they become a main sequence star. That means they've shifted into a position where they fall along that diagonal line on the HR diagram. And we call them a main sequence star. What the hell is this? The sun is today a main sequence star. What does that mean? What does it mean if we plot the sun's temperature versus the sun's luminosity, and we find the sun along this diagonal line called the main sequence? Does anyone remember? No? All right, maybe I need to put some context here. Stars can be found in a number of places on the HR diagram. Today, we want to talk about stars that live down here, and we want to remind ourselves about the stars that are up here. Your lab is about stars that are right there. But first, you have to remember why most stars are found along this diagonal called the main sequence. What's the significance of that? Maybe you should look at that table in your notes. Help me? Oh, sorry. Yes, the proton-proton chain, says Kaitlyn, the PP chain, okay? But what does that mean, the proton-proton chain? What's happening there? Kaitlyn, you gave me the specific reaction, but my point is you're kind of missing the bigger picture about what's going on there. No, you guys got nothing. This makes me want to give you a final exam. See, this is the kind of shit that makes me want to give you a test. When you're with me, then I think, well, you don't need a test because you know everything. And when you know nothing, that makes me think you need the, I was trying to give you the carrot. You didn't want the carrot, so now you're going to get the stick. Okay, that's how this works. Okay. Someone's got to work with me here. Okay. The importance is hydrogen to helium fusion. That's what the proton-proton chain means. And there are many ways to do there's a couple of ways, few ways to do hydrogen to helium fusion. But typically low mass stars use, as Kaitlyn reminds us, the PP chain. I didn't make that abbreviation up, astronomers did, okay? So then they go into a new stage of life. How long will the sun live on the main sequence? How long will the sun, I keep saying live, I'm personifying the sun. It's not alive, it's a ball of plasma. But they go through a life cycle just like living organisms do. Hydrogen to helium fusion has a time limit. What is the length of time our sun can do this on the main sequence? You had to calculate this for one of your homework problems. You got to know some things. Damn. One of the things that makes astronomy, okay, 10, and Elijah, what is that translated to in English? Just say it loud, say it proud.
Is it a billion?
Yeah, well, it's 10 billion, right?
Yeah, that's what I meant to say.
Okay. 10 times 10 to the 9 is 10 billion years, okay? What does the star do when it runs out of fusion? We've had this discussion, but maybe you need some, you definitely need some reminding. I can already tell from this, the way this discussion is going. Arunsak.
Does it begin to collapse on itself because it's no longer pushing out that thingy?
It's not so simple. When you say it collapses on itself, you mean the star is like infalling, right? But the star becomes separated into two components. It's not as simple as the whole star collapses. That's what you would think would happen. Normally, fusion puffs out the star, gravity squeezes the star, they come into balance and it has a fixed radius. You would think when you run out of gas, the star would collapse, but something much more complicated happens. We need to look at a diagram again. This will help remind you.
It becomes a red giant.
Becomes a red giant. So in a way, what Arunsak said was half right, but very much wrong, actually. Arunsak, this part of the star begins to collapse on itself. The core certainly collapses, but that tends to funnel fusion into a thin little hyper hot shell that pumps out so much extra fusion for a short period of time that what the star really does is it puffs out. Except it's not really fair to say the star is collapsing or the star is puffing out, because there's two stars in one. There's the outer envelope of the star, which is growing into what Kaitlyn calls a red giant. Then there's the core of the star, which is squishing in on itself and collapsing, okay? And red giants kind of have three different phases, and we kind of need to talk about them today because our lab is about the second phase of red giants. The red giant phase is eventually what will happen to our star. And there's sort of three different stages. I'm going to use Roman numerals now that I've brought up the Roman Empire. Well, Christopher, that's certainly a morbid, yeah, like a dead body bloating up as it decomposes, except then it shrinks and then it expands again. So it's even more complicated than that. Halloween has long come and gone. Okay, so, all right, so let's do stage one. Stage one is where you have hydrogen shell fusion. I'm going to use a fancy word, an inert helium core. Inert basically means you're not active. If you sit on the couch playing your PS5 all day, Austin, then you are inert. You are not active. There's no fusion at work, okay? So there's an inert helium core. And we have an expanding outer envelope. And I'm going to shorten that to an expanding envelope. I would love, wait, you get to drive around and sell PS5s? Will you sell me one? All right.
Cool.
Okay.
It's
Hydrogen.
only 1,100. So
Wait, say that again?
they're only 1,100 for me. So
1,100. What? That's
yeah,
cool.
everyone said I have a whole bunch if you need one.
Wait, you're not one of those guys who goes onto the Walmart website and like buys them all up and then resells them. Are you like one of, who the hell are those people? Why don't they have a job? Or
Well,
why?
I try to be those people, and we don't have a job because first of all, I got laid off because of COVID. Second of all, I make a hell of a lot more money doing this with unemployment than I do
Okay.
working. So
You know what? Fair. But wait, so do you have like a little internet bot? No, I'm really.
I don't have any bots,
I'm kind of
but
picky
I
in
have
my
plenty
video
of
games.
friends who do.
I shouldn't be playing any video games, but sometimes they fill a little hole in your soul, and sometimes you need to.
For
Okay. Anyway, so, but I'm very, very picky, guys. I'm not going to be doing a dance with you on Fortnite or something, okay?
Professor, I'll sell you a PS5 for the low if we don't have a final.
All right, we could talk about it.
Okay.
I can't show you a clear up-close picture of a red giant star. Why can't I? Why can't I show you a picture of a red giant? I mean, I do have one picture, but you're not going to like it.
I know why. I know why.
Why, Arunsak?
It's because they're not bright enough for us to capture them.
False. I
Right?
can see Betelgeuse with my naked eye in the sky tonight. It's bright enough for me to see with the unaided eye. I can certainly see Betelgeuse with a telescope. It's not about bright enough. Bright enough is the wrong thing. It's about, you don't see distance, Austin. That's the wrong way to talk. That's the wrong way to talk.
Well, because of the angle, you see angles, and the angle
yeah.
is too small. It's
That's
not a
right.
visible
It
angle.
doesn't have the right angular size. It
Not
turns
bright
out
enough.
that there's one other star besides the sun that we can resolve with a telescope, and it's Betelgeuse. and you really have to work hard at it. You're not going to like this picture, but let's show it to you. I think I might have shown you this picture before. Betelgeuse. Wikipedia has our best image of it, which it's just barely resolvable as a disk, but this is what Betelgeuse looks like to our best telescopes. Obviously, that's a really cruddy picture, and that's the best picture of a star that we have, more or less, outside of our own sun. How the hell do astronomers know so much about the stars? They work it out in their minds using the HR diagram. The reason the astronomers are obsessed with the HR diagram is it lets your mind go on a journey about what stars are doing. Now, first of all, you have to be crazy enough to care about stars. You have to look up at those twinkling lights in the sky and say, what the F, what's going on? What's it all about? Elijah, I see your cat and it's funny. Your cat's poking into the screen there. If you want to know what stars are doing, you can't just take a photo of them. So you have to look at the HR diagram. Let's look at what happens to the sun during that first phase. The reason why we know the sun's radius is expanding is we see other stars that are like the sun, and we see them leaving the main sequence and driving up the so-called asymptotic red giant branch. Remember, class, that temperature increases to the left, luminosity increases up, but because there is a relationship between temperature, luminosity, and radius, the radius of a star grows diagonally to the right. These are the kinds of things I will ask you a test question about if we have a test, okay? So I think it's fair game to warn you now. So if I see the sun evolving like this up the main sequence, if I see the sun doing this, I know that its radius is growing and there's a change in its fusion pattern. During this first stage, the first stage happens just along this branch here. We can see the sun's radius growing, growing, growing. Guys, what's happening to the temperature of the star during this phase? Arunsak's got it. The temperature is dropping because it's moving in this direction. Why would the sun's temperature be dropping as it turns into a red giant? Can someone explain that to me? There's a simple explanation for this if you can think it. Do I have that cartoon picture again? Where is it here? So I just went from a star like this that had fusion all throughout its core to an expanding star with a contracting. Why would this be cooler?
Is it because
It's not
it loses
fusion.
mass?
It's like
Hold on. Let me take you guys one at a time. I heard Christopher and I heard someone else. Who was the someone else?
That was Cameron.
Cameron, can you say that again?
I said it loses mass.
It does not lose mass. Eventually, the star will lose mass when it disconnects from itself, but it's expanding. What was your thought, Christopher?
it's not in fusion, so it's like it's, I guess, losing energy.
I wouldn't say losing energy. That's not. There's something much.
Or is it
simpler.
like the energy is kind of just getting spread out as it expands, so it's like kind of not as neat.
Guys, it's a ball of gas. No, it's not using it. Stars convert matter into energy in the form of radiation. Check. Here's some gas. Wait, hold on. Let me reset this. Reset. Let's make our. I wish this was a spherical container. That would be really cool, but they weren't that creative. They did this for a physicist, not for an astronomer. So let's put some gas into here. Okay, let's see what happens when we expand the ball of gas. Oh, this is isothermal. What happens to my star as it expands? Why does temperature drop? It's because it's a ball of gas. It's like a piston in a car, right? When you pull it apart, when you open it up, whatever. As it expands, it cools. And by the way, part of it is because it's losing some fusion in its core. There's something to what you're saying there. It's running out of energy. Okay. I need to tell you guys some technical details now. The temperature at which hydrogen can fuse, I don't even know where I'm going to put this, okay? So hydrogen fusion occurs at a unique temperature. It occurs at a temperature of 15 million Kelvin. During phase 1 of a red giant expansion, the inert helium core is heating up, but it's going from 15 million Kelvin to 16 to 17 to 18, and it's ticking upwards. Eventually, you hit the temperature at which helium fusion can proceed. The temperature of helium fusion needs to go up to a key value of 100 million Kelvin. That's significantly hotter than the temperature of helium fusion. Do you guys remember the name of the process under which helium fusion proceeds? Do you guys remember the name for helium fusion? These are the kind, I don't think you guys should take the final exam if I offer this question, because there's a name of a nuclear reaction called helium fusion. I don't want to, I don't want to
Triple
beat you
something?
guys. Sorry?
Triple something?
Yeah, the triple alpha process. Okay, I can work with that. And when the triple alpha process kicks in, suddenly the entire core of your red giant turns on fusion, and it goes into phase 2. Phase 2, you might even debate whether this is a red giant or not. Phase 2 is what your lab is about today. It's called a helium fusing star, but they usually call it a helium fusing star. I'm going to call it a helium fusing red giant because I still want you to remember that it's in the red giant phase. Except it stops looking like a red giant. By the way astronomers figured this out is kind of amazing. They plotted the positions of thousands upon thousands of stars on the HR diagram, and they could see different stars that were one solar mass at different stages of their red giant life cycle, and then they had to piece all this information together. And they noticed that all of the stars stopped climbing right at this point, and they all abruptly turned around and started going like this. And the realization that they had was, holy cow, this here is the moment when helium turns on all in an instant. The core of your red giant starts cooking up its fusion reactor again. And then look what happens to the star. Arunsak, what's happening to the temperature as it turns into a helium fusing star? The temperature's going up. What is happening to the radius of the star? Feel free to help Arunsak, anyone. He answered the last one correctly, so I thought he might know. What's happening to the radius star at this stage, stage 2 of my red giant?
Looks like it's going down.
That's right, because if the radius grows
Right.
diagonal to the right, if you're heading in that direction, wait a minute. Why would the radius of a red giant shrink once I turned on fusion? This is so just not intuitive. I have a better slide for this. One that shows the different stages, or at least the core. It's hard to find good pictures for this. There's probably better ones now. I haven't updated this in a few years. This shows you the 3 stages that our sun will go through in a red giant. And we've kind of talked about it before, but you kind of need to learn it a couple of times. When our sun, they actually call this part of the branch the subgiant branch. And now we're here to talk about this part. When fusion, so here you can see the subgiant. You have, sorry, let's look down here. So this stage here, the subgiant, is when you're turning into a red giant. You have inert helium in the core and a shell, a very thin shell of hydrogen fusion. The collapse of the core causes the star to puff out. But once you get helium fusion in the center of your Tootsie Roll, suddenly the star starts to contract and shrink again. It shrinks because this star is not in hydrostatic equilibrium, but this star is. You'll remember that I told you that in a red giant, the core contracts, the envelope expands. Let's take some notes on a helium fusing red giant. You have helium core fusion. So the core of the star is fusing helium. There is still a thin shell of hydrogen fusion, so you're getting double fusion. Hydrogen shell fusion. And you get a contracting envelope, the star returns to equilibrium. And the star takes on a yellowish appearance, but it does something else. This phase of a star is often accompanied by an instability. These stars become pulsating variable stars. An example of which is the North Star, Polaris. You guys remember which star Polaris is, right? Sorry, I should leave that there so you guys can take notes. What star is Polaris?
North Star.
The North Star. What constellation is it in?
Canis Major.
Sorry, that's Canis Major is Sirius. The big
This is Orion, right?
No, it's in the Little Dipper, Ursa Minor.
Oh, Canis Minor.
Ursa Minor.
Ursa Minor, that's right.
Ursa's Latin for bear, minor is little. Little bear, the little bear. You know that you can see with your naked eye, you can see Polaris pulsate. Well, you won't see it grow and shrink on the sky, but you can see its brightness change. The period of pulsation of Polaris is roughly 1 month. And during a month, Polaris will go from a magnitude 2 star down to a magnitude 3 star and back in a 30-day cycle. And I know this from going out to the observatory, because usually what I do with students is when they come to visit my observatory, I'll take my laser pointer and I'll shine it up at the sky and say, hey, that's the North Star. And at different times of the month, it'll go like light pollution is so bad in astronomy that we can clearly see a second rank star, but the third rank stars kind of get blended in with the background light pollution. So at different times of the month, Polaris could be very hard to see or very easy to see. You can make it a personal project to keep an eye on it, and you can see it vary as well. It turns out that variable stars play a huge role in the science of astronomy for a bunch of complicated reasons. First of all, I want you to imagine what it would be like if you could take your flying saucer, sorry, variable star GIF, and you could travel to a pulsating variable star. What you would see happen, is this a good animation or a bad animation? There's one that I like. Yeah. This is what you would see happening if you could take a trip to look at a variable star. Over the course of a month, this star would no longer be in hydrostatic equilibrium, but you would watch as its radius puffed out and expanded and contracted. It's almost like a valve, or it's like an accordion that's puffing in and out. And that's got to be really weird and freaky. Our sun, could you imagine what would it be like if our sun did this? You would see it growing and shrinking on the sky every day with your naked eye. If you lived on an alien planet around a pulsating variable, first of all, I hope you wouldn't live too close, because that might not be good for you. And the luminosities of these stars change along with their radius. Now, if you ask me why this happens, that's a question that's maybe a teeny bit over your pay grade. It has to do with the ionization states of helium. Helium makes this little valve where the electrons get ionized when it's hot. The electrons can block a lot of light, the star expands, and then when it cools, the electrons jump back onto helium, and that lets the photons through and the star contracts. Eddington, the famous astronomer, was famous for not inventing, but describing the helium valve by which stars can pulsate. It turns out that one of Pickering's Harvard computers, a woman named Henrietta Swan Leavitt, was not only the first astronomer to discover pulsating variable stars, but it's interesting because she was a woman who was doing science long before the era in which women were customary to doing work in astronomy. She was part of Pickering's harem there of ladies who worked in the Harvard College Observatory. And her claim to fame, the reason why we remember her now, is because she was the first woman to catalog, observe, and chart these pulsating variable stars. And her work was a brilliant job in astronomy of showing us how we could use the pulsations as a tool to measure distances to objects in other parts of the galaxy and beyond. And today your lab is going to be to redo the work that she did probably in 1910 or something. Oh, really? Well, considering that she lived in Boston, Jesse, there is a crazy thought that your friend could be somewhere in the family tree related to Henrietta Swan Leavitt. So you should have her do a little genealogy project about that. Considering that Rhode Island is not too far from Boston, it's not totally outside the bounds of possibility that they're related in some way, which is kind of a cool thought. The Great Swan constellation is not named after her. The Cygnus the Swan Cameron goes back literally thousands of years. Like Arab astronomers in 100 AD would have known Cygnus as a swan. In fact, Alberio is Arabic for the beak or something. That's Alberio's the binary star that's in the eye of or it's the beak of the swan. So that unfortunately goes back, or fortunately goes back way longer than that. How much we're going to learn about how variable stars work today, but let me just try to quickly explain what she did because it's kind of cool. Henrietta Swan Leavitt discovered that there were different variable stars found throughout the galaxy. Some had periods of pulsations of 2 to 3 days. Some had periods of pulsations of up to a month or longer. She did this brilliant research project where she discovered the period of pulsation was related to the luminosity of the star. And I'm going to try not to bore you here, but I would like to, I think I need to go to this slideshow to show you the work. So I should have this up for today anyways. Okay, so here's Henrietta Swan Leavitt, and she's measuring the period of pulsation. And the way she does that, you can actually see it in the picture on the wall there. She's measuring the cycle of oscillation of the star and comparing it to its brightness. And as an example of this, let me kind of bounce around here. Bear with me. If you guys remember, you could actually see some of her work. This photograph is so cool for this reason. On the office wall at the Harvard College Observatory. Come on, you bastard, where are you? Come on. Here. I'm not exactly sure which one Henrietta Swan Leavitt is because I'm not always the best at picking out faces. It might be her there. But can you guys see there? She's cataloging Beta Auriga in 1889, and you can see the period of pulsation. So there's that. I bet this graph is still in the Harvard College Observatory library somewhere. It would be cool to put your fingers on that document. So she's measuring the period of pulsation of a bunch of different variable stars, right? And then what she did, the brilliant thing she did, was she made a famous plot that you guys are going to recreate today called the period-luminosity relationship. She discovered that it wasn't random, but that depending on what the period of your star was, stars with longer periods of pulsation tended to be intrinsically more luminous. Now, you guys have to follow along with me here. This is going to take a couple of leapfrogs. She discovered that if you had a period of like 3 or 4 days, your variable star might be 1,000 times the luminosity of the sun. But if you were like Polaris and your period was a month, you would then be 10,000 times the luminosity of the sun. Why on earth would that be useful to an astronomer? Because it's a tool to let you calculate the distance. Remind yourself that the way astronomers find the distances to stars is through the luminosity distance formula. They reverse the inverse square law, and they find that the distance to a star is its intrinsic luminosity over 4 pi b. Now the brightness, this is something that you can measure. And you can measure by taking a photograph or even just looking at the star, you can get its magnitude. But this, how the hell are you going to know what the luminosity of a variable star is? You can't travel to the star and surround it with a giant Dyson sphere and measure its total luminous output. Except guess what? Henrietta Swan Leavitt could. She was clever because she realized she didn't need to measure the luminosity of the star. All she had to do was measure the period of the blink, how long it takes you for the star to blink on and off. She could then compute the luminosity with her graph and thereby measure the distance to a star. Such a technique is known in astronomy as a standard candle. And I want you to write this down. A standard candle are tools that astronomers, a standard candle is an object of known luminosity or discoverable luminosity, an object of known luminosity, and it's used to find the distance to the star. Sorry about my notes today. I got to tell you a bunch of messy things, and I'm not sure about the best way to organize it. Why is this important? Well, let me tell you a little bit of an extra tidbit here. When people looked out onto the sky with telescopes in the 1900s, they would often describe what they called spiral nebulae, and triangulum would be an example of a spiral nebulae. That's what they called these things at the time. If I showed you this picture, what would you guys say this was? I guess I wanted a very simple answer. I mean, like, what are you looking at here? What is this thing?
Triangular galaxy.
It's a galaxy, Caitlin. That's what I wanted you to say. If you were Henrietta Swan Leavitt and you were doing research in 1900, they didn't even have the concept of a galaxy 100 years ago. They didn't know what the crap this thing was. In fact, there were two schools of thought. Some people just thought they were other nebulae of gas, like the ones that we see through our telescope, like looking at the Horsehead Nebula. But then there were some people, and namely one of them was the philosopher Immanuel Kant, who argued with no justification whatsoever. The philosopher Immanuel Kant, who you might have heard about, he argued that these things were island universes. That's what he called them, island universes. And he argued to astronomers that these things were external objects full of stars and gas, basically a different, they didn't have the concept of a galaxy back then, but he meant to say that these were separate from our Milky Way. No one could prove which was true until Henrietta Swan Leavitt came along. And this is why her work is so important today. This is how a bunch of boring bullshit, like looking at graphs and studying the radius of a star, can suddenly turn into profound philosophical questions. So famously, what happened, and let me see if I can find the picture. So there was this thing called the Great Debate in astronomy. And so Immanuel Kant says in 1755, I think those little spirals that you see in your telescope are island universes. But astronomers weren't convinced. This guy might be a famous philosopher, but philosophers sit around thinking. They don't take measurements. The debate went on up until April of 1920, when two famous astronomers, Harlow Shapley and Herbert Curtis, had a public debate between two camps of astronomers about whether or not galaxies would be spiral universes. It took Edwin Hubble, the famous astronomer in the 1920s, to discover a Cepheid variable star inside of the Andromeda galaxy, okay? I think he was during a wartime blackout or something where the skies were dark enough over Mount Palomar, and he picked out a pulsating variable in the outer spiral arm of Andromeda. Try to understand what that would be like. To resolve a star in another galaxy is a humongous feat. You'd have to zoom in on this little patch of sky and just barely pick out a little blip on your photograph. And he found that the blip was pulsating. He measured its period. He then used Henrietta Swan Leavitt's period-luminosity relationship, and he proved to his fellow comrades, his fellow astronomers, that the distance to Andromeda was 2 to 3 light years away. That conclusively proved to other astronomers that the Andromeda galaxy was not just a little nebula, but was a whole different galaxy external to our own. We've known about this for less than 100 years, which is so profound to think about. It wouldn't be possible without pulsating variable stars. So my whole point there, if you can forgive that long-winded story, Cameron, relativity was proposed in 1905, special relativity, general relativity in 1915. They definitely had the concept of the speed of light because that's what relativity is based on. So the answer to your question is yes, they had that concept, but I'm sort of talking about something different here. I'm talking about using variable stars to find the distances to objects. Variable stars play a huge damned role in astronomy as standard candles. This is me trying to bring you up to the forefront of what astronomers do today. Okay, there is now a third stage of red giants that we need to talk about. And then I'm going to try to move on to their death before this class ends. In fact, we need to do a little reorganization here. So I'm erasing everything. Let me take those notes again so that we have an organization for them. We were discussing the 3 stages of a red giant star, at least for a low mass star. There is stage 1, which is called a subgiant. There's stage 2, which is a helium fusing star. And the helium fusing stars occupy a region known as the instability strip on the HR diagram. This is where you get, there are different types of variable stars. Probably one of the most famous are Cepheid variables. We'll call them pulsating variable stars, okay? And remember that during the second stage, you have helium core fusion and you have hydrogen shell fusion. So you have a double burst of fusion. Do you guys remember what helium fuses into in the triple alpha process? Helium fuses into another particular element.
Carbon.
I'm sorry?
Carbon.
Very good. Those are the kinds of questions, if we end up doing an exam, I'm going to ask you that. I'm going to say during the triple alpha process, no tricks. Helium fuses into what element? Hydrogen, oxygen, carbon, iron. And it's your job to pick the right one. Who answered that question?
Cameron.
Cameron, you're ready for the final exam, or ready for 1 out of 100 anyways. Okay. So helium core fusion is helium into carbon. Unfortunately, or fortunately, actually it doesn't really matter for us because we'll all be dead. The sun will never be able to fuse carbon into a heavier element. That is the last stop. This is the last element for low mass star fusion. If you want to know why, it's because the temperature for carbon fusion is 600 million Kelvin. That is so insanely hot that our sun just does not have enough gravitational matter to squeeze the star above that temperature. We know that our sun could never fuse carbon into heavier elements because there just is not enough gravity associated with our star to squeeze that central piston up to a high enough temperature. So put a big red X. So for low mass stars, it's not possible. In fact, it's going to turn out that only the highest mass stars are going to be able to go beyond this point. Based on what happened during the subgiant phase, remember that for a subgiant phase, you had inert helium and hydrogen shell fusion. Okay, this might break your spirit bank, but let's just try it. Can you guys predict what is going to happen in stage 3? When our sun uses up all of its helium core fusion? What will stage 3 of our red giant look like? Maybe is that too vague a question, or is it just too hard a question? In this one, you had an inert helium core and hydrogen shell fusion. In the
Is this low mass star, right?
The low mass star, yep.
Does it turn? Are you asking for what the next, like what it turns into?
Okay, I'm asking what will happen to the core of the star once it fuses all of its helium into carbon? I was really, I didn't phrase that right. I did a bad job. I was just saying, can you imagine what's going to happen inside the core of the sun when it fuses all of its helium into carbon? Like what?
The core shrinks.
The core will shrink. The core will shrink. Why don't we look at a photograph? I think a diagram or an illustration would be better here. Let's go to this slide, number 84. Okay. At first, you were fusing helium into carbon, but the carbon is starting to build up as a nugget in the center that's hot, but not hot enough for fusion. And eventually that nugget will grow and grow and grow until you hit this situation. You have an inert helium core, you have a layer of helium shell fusion, followed by a layer of hydrogen shell fusion. It's kind of like this Tootsie Roll with multiple layers, and the carbon nugget is building up in the core, and these shells get thinner and thinner and thinner, while the outer envelope of the star expands more and more and more. They call it a double shell burning red giant. And basically this star will puff itself apart like a smoke ring. It'll blow itself apart, not violently, but gently, very gently. And eventually what will happen is the star will distend. Let me click ahead here. And that's what it will become. This is the ultimate fate of our sun, to eject its outer envelope, the main layers of the star, as a giant, beautiful nebula. This is one of the most famous planetary nebulae in the sky. By the way, there's an unfortunate nomenclature here. People were observing these things long before they understood what they were. So some joker back in the day started calling these things planetary nebulae. What do they have to do with planets? Jack shit, okay? But that's the name that we use for the death of low mass stars. They're called planetary nebulae. And the Ring Nebula is one example of this. You can actually see this through a small telescope in the late autumn. I've looked at it many times. To get these colors, you have to take a very long exposure photograph. But look at all the structure to this. They're quite beautiful. Okay, let's take some notes on this. Just a minute, guys. Sorry, I'm sharing screen, but all my things are overlapping. Okay. Stage 3 of a red giant is a double shell fusing red giant. And this stage involves hydrogen shell fusion helium shell fusion, and inert carbon core. This is very important. This inert carbon core will turn into a white dwarf, and a very rapidly expanding outer envelope. Think about it, students. When the sun goes into its first stage of red giantness, when the sun becomes a subgiant, it will be capable of swallowing the planets Mercury, Venus, and maybe Earth. When it becomes a double shell fusing red giant, it'll probably swallow every planet in the solar system. In fact, I wouldn't want to live on no planet in a solar system in which a star was going into a double shell fusing red giant, because the plasma would basically just gobble up. Oh, yeah, sorry. Take some notes. I just got a couple of things left to do, and then we'll take a pause. Kaitlyn, let me know when you're done with a thumbs up. Okay. Arunsak, are you good? No. Okay. Okay. I need to wait. What do I want to do? I need to erase. I'm erasing. Finally, we get to the new chapter, the thing that we would like to discuss, the death of a low mass star. Remember that when our star was dying, there were two disconnected parts. And those parts were, if I trick back here, the core of the star, and then the sort of outer envelope. Why don't we draw a picture of it, okay? Let's draw a picture of the death of a one solar mass star. So here is the outer layers of the star, which I call the outer envelope. And then somewhere in the center of the star is the core. And most of the core of the star is made of highly compact, highly degenerate carbon. Surrounded by a layer of helium fusion. I'm just going to use blue for helium fusion. Don't ask me why, but the helium fusion is confined to a very thin shell, which is shrinking every day. The helium shell fusion is itself surrounded by a thin layer of hydrogen shell fusion. Let me just ask a simple, stupid question to make sure that you guys aren't totally lost. Why isn't there any fusion out here? Why is there no fusion here, but there's fusion here and here?
Because it's not hot enough.
Beautiful. I just wanted to make sure that you guys understood that. Okay, Kaitlyn, just keep with me for a sec. It's hot enough for fusion in this ring. It's hot enough for fusion in this ring. How about in here?
No, it's not hot enough.
How hot would this need to be?
Like, hold on 1 second. I have it written down.
10 million Kelvin, maybe?
No. 15
100
million.
million Kelvin.
That's for helium fusion.
Oh, what is it then? 15. Yeah, 15 million Kelvin.
Nope. 15 million for hydrogen, 100 million for helium.
Oh, that's carbon. I don't know.
Oh, is this the billion, the 100
Not
billion?
billions. 600 million.
Oh.
Okay. Carbon is 600 million. There's no. Yeah, we can't do that. The sun can't do that. If you meditate on what's going to happen, eventually these thin shells are going to get used up, and you're just going to leave behind a nugget of degenerate carbon. And meanwhile, these stars just begin expanding and expanding and expanding, and something funny happens. The star never ceases to expand. It basically expands itself apart. And that's how you end up with the ring nebula. You guys, planetary nebulae are some of the most beautiful things in all of astronomy. Maybe we'll end our lecture on a little picture show, and we'll get back to this next time. Hold on a second. So probably one of the best examples of, you don't get to see a star doing this very often. And one of the most famous examples of a low mass star that is expanding itself to death is that beautiful nugget known as Eta Carina in the Eagle Nebula. This is basically what our sun will look like maybe 6 billion years from now. It'll be a short window in time, maybe a period of a few thousand years or more, in which the star is just puffing itself to death. And these strong stellar winds are just blowing out the outer envelope into space. This is such a rare picture because it's such a short window of time that you just really have to get lucky to be able to catch a nearby star doing this. Most stars are not found in this stage. What it would look like is it would kind of look like a progression in these stages. Main sequence, red giant, and slowly the star would just start to kick off the outer nebula until it just cooled and became a bright emission nebula around us. So this is basically the idea. And that means there are two things left behind when a low mass star dies. The outer envelope, this part, will become the planetary nebula. We'll take notes on the board on this in a second. And this little bugger in here, this becomes a very unique sort of star called a white dwarf. And we can actually observe some of these things in different places in the nearby galaxy. I'm going to erase this picture here. The end result is two parts. The outer envelope of the star comes, while the inner core of the star becomes a white dwarf. A white dwarf is the exposed carbon nugget that's left behind. It's basically a carbon, I hate to use this word, but husk. It's like a dead nugget that's left behind. In our next lectures, we will explore the nature of the white dwarf, why it's weird. We'll also explore what happens to the death of a high mass star. So we're going to have to kind of do this again, although you'll be a little more prepared for it. Let me end the class before we do our break before lab. I would just like to show you guys a tour of some of the most famous planetary nebulae in space. And these are ones that we can observe with basic telescopes in our own backyards. The Ring Nebula is one of the most famous. Here's another beautiful one called the Cat's Eye Nebula. Yeah, Arunsak, what are you thinking?
Wait, go back to that last one you just showed, the planetary one.
These are all planetary nebulae. Yep.
That one. Okay, never mind. I thought I couldn't see the white dwarf in the middle, but I could see it now.
I have to tell you something, Arunsak. Oftentimes I lie to my students and I tell them that this is the white dwarf at the center. And I do that to make them feel better. The reality about this Arunsak is that's just a background star. The white dwarf has such a small radius that at this distance of several thousand light years, you can't actually detect it unless with a very, very powerful telescope. So that just happens to be a star that's in the background. I know it's kind of lame, right? That's why I usually just lie, because it's funner that way, to lie to you guys. Okay. Anyways, this one might actually, I don't think this is a background star. I think that could be the light from the white dwarf. Sometimes you can see it, sometimes you can't. This is the Cat's Eye Nebula. This is the Eskimo Nebula. I've seen this one from the Jacobi telescope. Look at this one, the Ant Nebula. Do you guys have any idea why it might be making this kind of lobed structure instead of expanding out in a shell? Can you think of a reason why it might have this dipole pattern, so to speak? Why would
Is
the
it
ant
like
So, because
one
it's
of
two
the?
why is it segregating into two parts like that?
Is it one of those like really, really big stars that's like
It's
exploding
definitely
or
a
whatever?
binary.
It's not a binary. Nor is it a big star. This is a low mass star.
Is there some sort of like other gravitational pull working on it?
It's not gravitational. We had a rule as graduate students when I was at Boston University. Anytime one of the more senior professors would ask you a question like the way that I do to you, and they'd try to mess you up, if you didn't know the answer, you would just say magnetic fields, because usually you would write, you just say, it's probably magnetic field. So what's probably happening is you can even see the dipole structure, just like the Earth's magnetic field. This star probably has powerful magnetic fields, which is trapping and constraining the plasma, forcing it to expand out along these two jets. We see this structure with some planetary nebulae. They tend to have an hourglass. In fact, one of them is called the Hourglass Nebula. This is the Twin Jet Nebula. These are all different types of planetary nebulae. When low mass stars die, they die beautifully. Here's the Southern Owl Nebula. Look at this one. This is the Helix Nebula. This is a beautiful photograph. By the way, this is one that I took with some students a couple of years ago. The Dumbbell Nebula, as seen from Jacobi's 16-inch. We actually took this image. It's the higher resolution ones look like this. So, you know, our picture was we only had time to take about 20 or 30 exposures and stack them, but I was proud of it. Okay, well, we've learned a lot today. Let's pause, take a break, and in 15 minutes or so, a little over 15, we'll come back. Maybe we'll start it. We'll give ourselves 20 minutes. At 1:15, we'll start our period luminosity lab. Does that sound like a plan? All right.
Sounds good to me.
See you guys in a little bit. All right. I just have to unpause this for a second so we can see the newest member to the class there. You ready to do some work, Kitty? We're going to plot some points. Oh my gosh. Okay, guys, give me one. Okay, Astronomy 1020. Welcome to our 11th lab. Lab 11 is the period luminosity relationship. We are going to follow the footsteps of Henrietta Swan Leavitt, who you learned about in today's lecture, who discovered that she could use the pulsation of a Cepheid variable to determine its luminosity. Then she could determine the luminosity, use the luminosity to determine the distance to the variable star. And if that variable star happens to be in a nearby galaxy, such as the Large Magellanic Clouds, well, then that variable star can be used to measure the distance to an external galaxy. The Large Magellanic Clouds are, or the Large and Small Magellanic Clouds are small galaxies that orbit the Milky Way. Just to make this more interesting, large and small we cannot see the Magellanic Clouds from the northern hemisphere. They can only be seen from the southern hemisphere, but supposedly they're quite beautiful. You can actually see them with the naked eye, and they look like small irregular blue galaxies on your sky. One of the reasons I would always love to be able to observe from the southern hemisphere would be to see for myself the large and small Magellanic Clouds. Anyways, we're going to use a variable star in the Magellanic Cloud to determine its distance. But before we can do that, we first have to recreate Henrietta Swan Leavitt's period-luminosity relationship. Okay, here I need to tell you some truths that I did not share with you before. During the course of today's lecture, when I taught you about the period-luminosity relationship, let me just get the right graph here. I told you that Henrietta Swan Leavitt used the period of a variable star to determine its luminosity, and that was true. Oh, shoot. Sorry, guys. Brain not firing on all cylinders today. Where are we? Here we go. 43, that's what it was. The thing that I didn't tell you is that it's not actually the period that she plotted versus the luminosity. It is the log of the period. And for today's lab, we need to have a discussion about logs. I ain't talking it's big, it's heavy, it's wood logs. I'm talking that mathematical function log. So which one of you math experts knows what the function of log is? No one? Someone's got to know. I need some scrap paper for today's business. Who knows what a log is? Arunsak, you seem to know things about math.
From what I know, it's that it's not like one. It's like pi. It's constantly just, you know, going.
All right.
That was wrong, wasn't it?
Yeah, pretty much. Okay.
It's like
So-
the logarithms, right?
Yeah. So what does a logarithm do? What does the
Like
log of x
it's a
achieve?
function, and it like
And what's the purpose of the function? I'm going to go back, find all of your high school math teachers and personally depose them from their chairs. Okay. This is a travesty. Logs.
mine was a nice woman, but she wasn't very good at teaching, so that's fine.
Yeah, well, math people ain't known for their personalities, you know. It's one of the. Okay, so yeah, that cat. So listen, a log is a simple concept. If you're willing to listen to me and explain it right, even this cat wants to know about logs. Okay, the log was designed to solve this problem. The log of x equals some number, like let's say 100. I bet you guys know what x is in this case. I bet just because you're smart, you could tell me, look at this thing. I bet because you're smart, this cat could probably tell me what x is in this equation here, right? What is x? Oh, Jesus.
10. 1, 2, 2, 2, 2. My fault too.
Okay. X is clearly 2. How did you know that, Arunsak? Why don't we explain this to everybody?
10 to the 2 is 100.
Yeah, 10 squared is 100. So if I said 10 to the power of x equals 1,000, what would x be then?
3.
Good. And 10 to the x is 10,000. Keep going with me. Just play along. Play the game.
4.
And 10 to the x is equal to 100,000. What's that?
5.
Now, what if instead 10 to the power of x equaled 54321? What's x then? Suppose 10 to the power of x equals 50.
3.
Huh?
3.
It's not 3. 10 to the power of 3 is 1,000.
So 4.
10 to the power of 4 is 10,000. Your number is clearly bigger than that.
2.
So is it 5,000? 50,000?
What would x be?
10 to the power of 5.
10 to the power of 5 is 100,000. Your number is less than that.
Oh, never mind.
Use a log.
That's the idea. But hold on, Arunsak, before I tell you about logs, you could probably guess what X was between, right? X is clearly between two numbers. Are you with me? Arunsak is with me. Explain that to them.
Well, it looks like it's between 4 and 5, but we don't know exactly because all the random like 4, 3, 2, 1s. That's when you gotta use the log.
So Arunsak's point is that if 10 to the 4 is 10,000, 10 to the 5 is 100,000, our number should be somewhere between 4 and 5, right? Because our number is somewhere in between 10,000 and 100,000. Y'all with me? So here's what you do to solve the problem. You write a computer program which is designed to raise 10 to the power of every number between 4 and 5. Let me clear this out. So what you do is you write a computer program that will raise 10 to the power of 4.01, 10 to the power of 4.02, 10 to the power of 4.03, and you tabulate all the results in a log table. And then you turn it into a little computer program to reverse engineer. So the idea is you raise 10 to every power between 4 and 5, and then you find the number that's closest to 5, 4, 3, 2, 1. Should we try it? Let's take out our calculators. Let's do it. 5, 4, 3, 2, 1. And then all we have to do is hit log. It looks like for 10 to the power of 5, 4, 3, 2, 1, X is equal to something like 4.73. Nice, right? Okay. So now that you know this, it's time for us to do some work. Okay. Let's talk about this first page, 16-3. We have two groups of Cepheid variables. We have some Cepheid variables from some different galaxies. We know the log of their period. We know their period. We know the log of their period. And we know their absolute magnitude, which is kind of like the luminosity. Up here, we have a bunch of Cepheid variables that we've measured in zeta Persei. I think that's zeta, right? Or is that Chi Persei? Hold on. I have a little book here. In this pig pen of an apartment. This book got me through undergraduate and grad school. Chi. Yeah. Okay, Chi. So this is Chi Persei. And we happen to know from the text that the distance to the star cluster Chi Persei is 26,000 parsecs. Write that down. That's going to be important. Oh, sorry, not 26,000, 2,600 parsecs. I apologize. Okay. We've measured the period of pulsation of these four variables. They've taken the log P for us. We have their apparent magnitude. And we can I'm going to try to do two things, class. Oh, shit. First of all, I'm going to undo my lock. And second of all, I need to, wow, my battery is low. Hold on. I need to go to my display. And I need to never, is that auto lock that I want? Yeah. I need to never auto lock. And then I need to plug this bad boy in. Fudge. Is this? Okay. Okay, that's good. And now here. Sorry, guys. I just realized that I'm going to need kind of a better setup for y'all here. Hopefully this doesn't tip over. All right. We need a formula to calculate our absolute magnitude. Our absolute magnitude is given by the apparent magnitude plus 5 minus 5 times the log of the distance. This is an old astronomy formula that relates the apparent magnitude, which is the brightness, to the absolute magnitude, which is the luminosity. Okay, the distance is always going to be, hold on, let me remove my notation stuff here. The distance will all, sorry. I'm just trying to get this all framed in the screen right.
Professor,
Yeah.
should I be writing down all those things if I don't have them printed out? Or everything right there?
Well, you need to write down these things. You need to write down log of period, and you need to write down absolute magnitude. Those are the absolute necessity things. This other stuff is less important. All right. Do you guys have calculators handy? You got to do some math today. All right. Let's try to calculate the first absolute magnitude using the first apparent magnitude, which will be plugged in there. And the distance will be plugged in there. I'm guessing you guys probably cannot execute this without screwing it up, right? So do we want to do one together using order of operations?
Yes.
Remember that exponents, which log is an exponent, so to speak, is more powerful than multiplication or addition. So we start with our apparent magnitude, 8.36. Then we do plus 5. Then we do minus 5 times, and here we're going to get weird. We're going to put in the distance first, 2,600. Then we're going to do the log of that. And since we already hit the times, we're going to hit equals. Our first absolute magnitude is negative 3.71. Okay. Now I want you guys to get me these next three using that same same technique. Can you do that for me? So why don't you guys go for the next one?
Where's your calculator?
In my thing, in my briefcase.
Where's your-
Is your girlfriend keeping you on task here, Austin?
Yes, I'm looking for the calculator.
Okay,
No.
yeah, you keep him paying attention here.
She's on task for me.
I hope she's not doing it for you, because then I'm going to give her your A.
She could have one. She deserves an A every once in a while. All those.
Okay, who's got the next one for me? I'll fact check you.
9.28.
I got 4.1.
Got negative
4.1,
4.8.
negative.
Yeah, Stacy's got it, and Caitlin, I think you probably rounded it to two. Caitlin, for this one, we're going to keep 3 sig figs, but remember, it's negative,
Oh.
Caitlin. So
Yeah, negative 4.08.
yeah, there's no way you could have known I wanted 3 sig figs there, but that's fine. Okay, get me the next two, please. I'd like you guys to do it. What do we got after that? Looks good, Stacy. Stacy got
Negative 4.51.
excellent. Let's do Cassiopeia, SZ Cassiopeia.
Negative 4.88.
Nice, Christopher. Okay. Now we're ready to do some plotting. Y'all gonna love this. Too many damn things. Put a star next to log P. Put a star next to absolute magnitude. And then down here, we're gonna have to plot these points as well. This is gonna suck a little bit. Oh, by the way, can we all get our names on these? Please put your name, lab number 11, AS1020, and then your section. Thank you much. Okay. All right, does everyone have this stuff? I'm now going to take, we have to recreate Henrietta Swan Leavitt's period luminosity relationship. But remember, what we're actually plotting is the log of the period versus the absolute magnitude, okay? Now we're gonna have to use our best graphing skills here. First of all, what is each tick mark on the y-axis worth? Can you guys tell me that?
Uh, 0.1.
0.1 magnitudes. How about down here on the y-axis, on the x-axis rather? Y'all remember how to do this, right? How do you
Each tick is 0.02.
Yeah, that's right. So this for log period is 0.02 per tick mark.
Hey, your camera is really laggy, just so you know.
I know, I'm really sorry about it. I don't know why it's sucking so bad. Okay, hold on a second. Guys, I don't know how I did this before, because I've done this lab before, only once or twice, but I'm just having trouble with my setup and my lifestyle here. And that goes for more than just this lab, I'm afraid. 0.02 per tick. Okay, so let's get our first one down, and hopefully this will go faster as we go. Our first data point is 0.73, 3.71. I want you guys to watch how I do this. This is 0.6, that's 0.7. And if we want 0.73, that's 0.7, that's 0.72. Oh, shoot. Sorry, you guys can't see this. That's 0.7, that's 0.72, that's 0.74. So 0.73, I'm gonna use a little memory tick there, should be right there. And that's gotta correspond to negative 3.71. Sorry, I didn't charge up my phone enough, so my cable is sort of tugging it off the table here. I might need to try to tape this down. Okay, negative 3 point, it helps to have a ruler when you do this, because the ruler can guide you horizontally. This is negative 3.71. So that's negative 3, that's negative 3.5, negative 3.6, that's negative 3.7, and just a smidge above that. So I'm going to go to the intersection of 0.72 and 3.71. Make a dot right there. Okay, let's move on. The next one is 0.74 and negative 4.08. So 0.74 is right next to 0.73. It's right there. And I'm going to use my ruler to guide me to negative 4.1. It should be just below there. So we're going to be right next to this dot, but we're going to be basically right at negative 4.08 is really close to negative 4.1, but just below it. Are you guys following this? I don't know what your plot skills are like. Kaitlyn, talk to me then. I don't want to go too fast or too slow, so I need some guidance from you guys.
Yeah, the camera's still kind of choppy. What was I gonna say? I'm sorry.
Well, that's okay, but
I didn't see how you plotted those. I'm sorry.
okay, can we just do it again then? Because part of it was my camera wasn't in position and part of it is the lag. So let's just do this again. Do you agree, Kaitlyn, that 0.7 is halfway between 0.6 and 0.8? Okay, some person in our class has determined that each little box is worth 0.02. That makes this 0.7, 0.72, 0.74, 0.76, 0.78, 0.8. Did that make sense? That means 0.73 is right there, right? And remember what I'm plotting, Kaitlyn. In our first graph there, I'm plotting log p 0.73 versus negative 3.71. Now, the way I did this, and these are skills for life, by the way. These are not just astronomy skills. These are just skills. I took my ruler and I shimmied it down first to negative 3.5. Then I went up to negative 3.6. Then I went up to negative 3.7. And I guided my pencil from 0.73 all the way up to negative 3.71, and I put a dot there. The next data point was at 0.74. First, I make a memory tick at 0.74, but the value was negative 4.08, which I know is wicked close to negative 4.1. So I put my ruler at negative 4.1. I went from 0.73 over to the next box, and I put my dot there. Let's proceed. The next data point is 1.04 log P and negative 4.1 absolute magnitude. So I'm going to go to 1.04. Let's see. That's 1.02. That is 1.04, right on the line. Then I'm going to go to negative 4.51. So this is negative 4.5, which is pretty darn tootin' close. Maybe just a smidge above it is where I want to be. And then I'm going to go from here, up, and negative 4.51, bam, put a dot right there. Okay. All right, next one up is 1.13. So that's 1. Oh shit, sorry. Okay. That's 1.1. That's 1.12. 1.13 is right there. Okay, so 1.13 matches up with negative 4.88. Here's negative 5. Here's negative 4.9, which is just above negative 4.88. So I'm going to go 113, and put it just above, or just below, rather, negative 4.9. Wait. Yeah, exactly. Now we have to go to the lower part of the table down here. So we got to plot all these. 0.49, negative 2.09. We'll try to speed up our game if we can. Okay, 0.49 is right after 0.48. And negative 2.9 is easy to find. It's right down here. Do you guys see how I'm using memory ticks to guide me? The memory ticks help you keep your brain straight, especially if your brain is old and soggy and full of whiskey like mine is, okay? Now, let's see, 0.71 is right there, just half a block from 0.7. And then that corresponds to negative 3.84. So negative 3.9 is here. I need to go a little bit below there. Okay. Try to position this good for you. Next one is 0.65. 0.65 is halfway between 0.6 and 0.7. And then negative 3.78 should be really close to negative 3.8. So there's negative 3.8. Put it just below there. We're filling in these data points. Now we have negative 0.83. That's 1.5 blocks from 0.8. And that's going to take us to negative 3.63. Negative 3.6 is right about there. I'll go a little bit above it. And pow. There's my data point. Now we're going to go to 0.9. That's easy enough. 0.9 is right here. And 0.9 corresponds to negative 3.62. There's negative 3.6. We'll go a smidgy widgy above it. And 0.9, negative 3.62 is somewhat awkwardly right about there. 0.99, which is half a block from 1.0, will match up with negative 4.27. That's basically negative 4.3. 4.3 is this line here. Sorry. Trying to keep this all. So 0.99 negative 4.3. Bam. There's my dot. One more to do. 1.62. Whoa, 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 whoa. We got to go way the heck over here. We got to go to 1.62. It's my last one, so I'll make a big memory tick. And negative 6.25. Wow. Negative 6.2. There's negative 6.3. Don't want to drift. And I got to go up all the way halfway between those two boxes. Now, we've completed our period luminosity graph. Now that might look a little bit messy to your eyes, but to an astronomer, that looks like a least fit squares problem. That looks like a straight line of y equals mx plus b. Yes, I know the data is noisy. Real data is always noisy. Let's see if we can make a best fit line to draw through this with a ruler. And I'd like you guys to play along with me here. The best fit line is the line which minimizes the distance between the data points and the line. So you're looking for that line which will have the minimum deviations between all of the points. I'm trying to zoom out here. I need like a macro lens. We will not bias it towards the origin. We do not want to include that because that's not a real point. I'm going to put one at the top point up here. I'm going to put, sorry guys, I'm just freaking running out of room here. Okay, let me try this again. I'm going to put my ruler up here at the top point. I'll put another ruler down here at the the other side of the bottom point, and that's probably my best fit line because I'm using the first and last point, but I'm keeping the other points close to the line. And I'm going to draw this all the way up and down. I'm going to go back and forth a couple of times. This is what our best fit line looks like. Think you guys can reproduce that for me? Use the top and bottom points to do it. How's this looking on your end, everyone? Wicked awesome? All right, we're going to put this on ice for a bit, and we're going to go, now that we, yeah, Emily, are you seeing this here? Emily, that's what I'm trying to do right now. Can we move on? Okay. So let's put that on ice. Now that we have a period luminosity relationship, we can go out and look into the Magellanic Cloud to find another variable star. And this is intense. This is a plot of magnitude as a function of time and days.
Talking about everything else, Austin.
I think someone's unmuted. I can hear you arguing with your mom or something.
What was your point about everything?
Who is that?
Like the
I mute them?
I understand that, but like they're like on.
Hey, Austin, STFU, buddy.
Oh,
Thank you. Could you mute? Okay.
sorry, everybody.
That's all right. That's all right. Hold on. I just dropped my pencil. Okay. Guys, I want you to be careful on this plot. You have to be very careful. Ah, fuck. Wait. Oh, damn it. Okay. Sorry. I'm having some difficulty with my lifestyle here today. Whoop. Yeah, there we go. Guys, I want you to be very careful with this plot. Do you guys see how it gets smaller as it gets taller? That's gonna mess you up. Okay, someone tell me, what is each tick mark worth on the y-axis? Talk to me, peoples. Interval divided by the number of boxes. Here's the deal, guys. I already know how to do this.
0.02.
Very good. So it's 0.02 per box here. Arunsak, since you're down to sort of play tennis with me here, what about the y-axis?
The X,
Yeah, sorry. Yes, the x-axis.
0.1.
All right. So our first data point is 1.28 and 15.83. Oh, we're going to make our lives just a little bit more simple here. We are going to round to the nearest tenth. So let's play a little tricky game with each other. Instead of 1.28, we're going to make it 1.3. Instead of 1.37, we're going to make it 1.4. We'll round that to 1.6. And by doing this, we're going to make our plot a lot faster. That's so we can get done and be done with this sooner. Does everyone like that? That will speed this thing up and it'll probably give us the same results. So we're doing 1.3 and 15.83. So here's 1.3. And hold on a sec, guys. I got to get up working my feng shui. Okay. I don't know why it seems so zoomed in, but it's just, and this cable is kind of, I'm going to go without the cable for a second. Okay. 1.3 and 15.83. 15.8 is here. 15.83 is down. We have to go down to 15.82, 15.84, and that in the middle is 15.83. So make a line for 15.83. I'll go to 1.3, bam. And I'll make my data point. All right, that's a fuzzy, by the way, sorry. 1.4 and 15.95. Here is 1.4 and 15.9294 and 95 will be just below 94. So doot, and halfway in between, bam. And that's 15.95. Now we're at 1.6 and 15.59. This is 1.5, this is 1.6. 15.59, we have to zoom up. There's 15.5, 5.2, 5.4, and we're almost at 5.6. Go. Next up, 1.8 and 15.26. 1.8 is right here. 15.26, 24, sorry, 22, 24, 26 is right there. Okay. 2.2 is next. 2.2 is right there. 15.20 is right on the line. Easy peasy pie. Don't drift. Okay, I didn't drift. 2.3 and 15.23. So this is 2.3 and 15.23 would be 22, just below this. Let's see, 2.7 and 15.32. This is 2.7, 15.32 would be there. Bam. 3.2, 15.41. there's 3.2. 15.41 is halfway in between this box and the next box. Okay. 4.0 and 15.51. We might want to start checking these off. 4.0, 15.51. So there's 4.0, and 15.51 is halfway in between 15.5 and 15.52. So we'll put that bad boy right there. Let's see. 4.2, 15.56. So that's 4.2, 15.525456. The next data point. 4.6 and 15.7. 4.6 is right there, and 15.7 is this big dark line. Drag them up, knock them out, put the dot, bam. Okay, 5.2 and 15.84. There's 5.2, 15.82, 15.84. All right. 5.4, 15.84. So there's 5.4, and 15.84 is 2 ticks down from 15.8. There's our next dot. We have 5.9 and 15.85. There's 5.9, 15.8284, and just below 84 is 85. So that's halfway in between these two boxes. Okay. 6.0 and 15.93. 6.0, 15.9, 15.92, 15.94. Just below 15.92 is where we want to be. No drifting. Okay. 6.3 is 3 ticks over. 15.61. 15.6 is here. 15.61 is half a box below it. So I was at 6.31 and half a box below that. Our star is starting to brighten again. 16.5 and 15.3. Sorry, 6.5 and 15.3. There's 6.5. And whoa, 15.3 is way up here. By that major intersection, you guys probably couldn't even see that. It's wicked high up. 15.3 is right there. 6.9 is there, and 15.19 is really close to 15.2. Oh, sorry. 19 puts it right about there. It's getting harder to keep this in my field of view. Maybe I need to do this. Nope, that don't work. I need to get a, you know what I need to get is I need to get a document camera. That would solve all these damn problems. Maybe I can just do, would this work? Ooh, hey. Wait, let me rotate this by 90 degrees. Oh, this is cool. This kind of works. Okay. Sorry. What are we at? We just did 6.9, so we're at 7.5, right? So 7.5 is there. And then we've got to go up to, shoot, it's hard to show this to you. 7.5 and 15.33. There's 15.3. There's 15.32. There's 15.34. So 15.33 should be just below this. So 7.5, and there's 15.3. Yeah. I'm starting to go stupid-eyed here. Going stupid-eye. Okay. 7.9, 15.39. So there's 7.9 right there. And 15.3, 32, 34, 36, 38. It's just below that. Okay, we're almost there. 8.65. 8. That's 8.7 pretty much. That's 8.7. And then 15.53. 15.52 is this line. Oh, it's kind of hard with 15.52 is that line. I'll go just below that. 8.8 brings us here to the next tick mark. That's 8.8. And that's 15.56. 15.52, 54, 56 on the nose. Okay. 8.9. 15.64 is 2 ticks below 15.6. (9.2) and 15.7. Last point, 9.2. Take. Okay, sorry. Hold on. 9.2 and 15.7. 15.7 is right on that line. 9.2. All right. Jesus creeps. All right, that's what we got. You guys see that? Looks like two little mountains, right? We got to make a best fit curve for this. Now here I want to tell you some knowledge I have. Cepheid variable stars don't have a perfectly smooth sinusoidal brightness. This is called a sine wave. They kind of have something called a sawtooth wave. They have a rapid rise followed by a long downset, and then another rapid rise and another long downset. You can kind of see that here in our graph. Now we got to make a best fit curve. You know, only Pee Wee Herman connects the dots, la 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 la. Most scientists have to make a smooth organic curve. And I want you guys to follow me while I do this here, okay? Okay, we're going to kind of not be pushed around by any one data point. We're going to see the pattern behind the noise. So we're going to go up through the peak. Then we're going to come down. We're going to go back up through the second peak. And we're going to come down. That's what our best fit line, our best fit curve rather, should look like. Can you guys do that for me? So did I lose you guys, or are you with me? What does this graph represent? I bet no one can answer that question.
Is
What does
that the way it expands and shrinks?
Right, but we're not measuring the expansion per se. We are measuring the, take it away, Arunsak.
Luminosity,
Brightness, the brightness.
brightness.
Okay. Arunsak, can you think of a way we could get the period of oscillation?
You take the peak and lows.
Well, it's the cycle is peak to peak, right? So let's
Right,
take
yeah,
our
yeah, yeah.
rulers. Hold on, I'm going to try to go back to this doc cam mode here. Let's take a ruler through our first peak. And we go from the curve, not from the points. The first peak looks like it's pretty much at 2. Okay, that's the first peak. And now we got to go to the second peak. Second peak's there. Notice I'm not using the point, but I'm using the curve. What's this value?
.8.
And this value over here is 2.0, right? So our period is the change in time between those two, which is 6.8 minus 2.0, or 4.8. And that's what we should put here for period. 4.8 days. To get the log of the period, we simply hit log. So type 4.8, hit log, you get 0.68. Now we have to use our period luminosity relationship. If I have a log period of 0.68, what should the absolute magnitude be? To do this, we need to go back to the graph that we made, the period luminosity relationship. Oops, I'm upside down. That plots log of period versus my absolute magnitude. Here's how we're going to do this. We're going to use the line. We're going to go to 0.68. I might actually just do this in another color if I have another color handy. Does this teal marker work? Okay, yeah. I'm going to use teal. I'm going to find 0.68, which is there. And I'm going to go right up to the line. Then I'm going to go over to get the absolute magnitude. My value looks to be about negative 3.5, excuse me. Everyone see how I did that? Okay. So this is negative 3.5. Now let me tell you what you were supposed to do next. You were supposed to find the average apparent magnitude. That would mean adding up all of these magnitudes, all 25 of them, and dividing by 25. I don't hate you, and most importantly, I don't hate myself enough to make you do that. So I've already computed the average, and I'll tell you that it's 15.56, and that'll save us a bit of time here, okay? Okay, now we have to get something called the distance modulus, the apparent magnitude minus the absolute magnitude, taking careful account of our negatives. 15.56 minus 3.5 negative thereof. You got to do the negative afterwards for this to work. 19.06. And as you learned in your last lab or 2 labs ago, we can convert a distance modulus into a distance. Let's go ahead and do that. To do this, we need the final page of this handout, which I hope to God I have. Oh my goodness. Did I not get the final page? What? Oh, here it is. Okay. Sorry, I got a little disorganized for a second. Totally unlike me, I assure you. Okay, this is a plot of distance modulus on the x-axis versus distance in parsecs. It's our old friend, the logarithmic graph. Remember this? So it was what, 19 point what? 19.06. So here's 19, 19.2, 19.4. Wait, sorry. 19.06 is really close to 19. So let's go up to 19. Once again, I'll use teal. Okay, it's actually, oh my God, this is really horrible. Do I have a magnifying glass here? Oh, sorry, it's a little smudgy wudgy. Cool. Optics are awesome. There. Ah. It's one line above that intersection. Wow, this is really hard to not screw up. All right. That's my value as best as I can tell. What does it look like to you? These are all 1,000. So 60,000, 61,000, 62,000. Let's go with 63,000 parsecs. And that number goes here. Shoot. Oops. Ah, come on. And thus we determine the distance to the Large Magellanic Cloud, 63,000 parsecs away. Okay, that concludes our lab. You should have this sheet with the Cepheid variable plot. You should have this sheet, period luminosity relationship. And you should have this sheet with the log P's and the apparent absolute magnitudes of your cluster. So, whew, excuse me, I'm looking for 3 sheets, okay? Before I stop my cell phone service here, does anyone need to see a page again? Tell me now. I'm going to stop the share. Well, goddamn, that was a bucket of fun. Okay. I'm glad that you guys did a little plotting with me. On Thursday, we'll learn more about the death of stars. We will do homework for chapter 18, which I believe is, homework number 12. Yeah. Hey, what lab are we turning this into? What lab number was this? 11. Okay. Please photograph it and upload it right away. Anything else?
Yeah, I'm sorry. I have 4 pages. Which, can you please go over which pages you want again? I just don't want to turn in, unless I can just turn 4 in and be done.
You can turn it for it. I was going to turn in the ones we worked on. This one,
Yep,
the first graph,
yep.
and the second graph. This one was part of the lab, but we didn't really write on it that much, so I don't care. Yeah.
Thank you.
Does that make sense?
Yes, thank you very much.
Caroline, it's nice to see you again. We've missed you. Okay. All right. I'll see you guys on Thursday, right? Peace
Thank
out.
you.
Bye.